My name is Kariuki Chege, so the pronunciation was fine, I guess. I'll talk about ionospheric effects on MWA EoR observations, and I am a PhD student at Curtin University, and my supervisors are Chris Jordan, Christine Lynch, and Catherine Trott. So the 21 centimeter signal is a faint signal, and for us to have a chance of detecting it, we really need to work on the calibration aspect of our observations. And the foregrounds are the main challenge because they're much brighter than the signal itself, several orders of magnitude brighter. And the effectiveness of any foreground mitigation challenge depends on how well we can model our sky, the beam, also eliminating radio frequency interference and the ionosphere, which I'll talk about in this talk. And it's very clear that precise direction independent and also direction dependent calibration of 21 centimeter signals is paramount. Now, going to the ionosphere, electrons in the ionosphere refract incoming radiation, and this refracted signal has these adverse effects on our images, where we see the sources shifting in the sky. And this movement is because the interferometer is measuring the phase changes in the incoming radiation lines of sight. And at lower frequencies, this effect is more enhanced, and that's a big problem for low frequency interferometers. And this is shown in this plot here, where we see that the offsets get larger at low frequencies, as shown with these lambda square feet. We can model this effect of the ionosphere as a phase screen, which is a thin phase screen, and it's shown in this cartoon here with the with the antennas of the interferometer at a certain height below the ionosphere. And we hope, by hoping that we can have a lot of these lines of sight, we can actually get a good idea of how the ionosphere is affecting our observations. And we are lucky that the MWA has a big field of view, so we have a lot of these lines of sight, and we can actually characterize the ionosphere itself during the process of calibration. Jordan et al. 2017 did this characterization of the different ionospheric activities at the MWA site. And he categorized this activity into 4 main types based on the source offset magnitude and the spatial structures in the ionosphere. For me, I wanted to be able to study these effects and how these ionospheric effects and the effects on the power spectrum. But we need first to eliminate all the other systematics. So in the paper I published this year, I made a simulation suite that combines different phase screens with the MWA array layout, then adding the sky model and calculating the different line of sight to all the sources in our sky, and also all the phase gradients that come from those lines of sight and other ingredients such as the instrumental response. We can get these ionospherically contaminated visibilities. Now, with these ones, we can then go ahead to calculate the power spectrum and see exactly how the ionosphere is affecting our 21 centimeter signal. And in this plot, we have a sort of many simulations taken all the way to the 21 centimeter power spectrum in one dimension. It tells us that the worst ionosphere, like in the bottom column, we can't really help much no matter how well we do the calibration. So in this case, I was asking the question, like, how can we improve our power spectrum by increasing the number of calibrators, basically the different directions in the sky, we correct for the ionosphere. And if the ionosphere is not extremely bad, we can get some improvements by increasing these number of ionospheric calibrators, is shown in the top row. And this can be done in both when doing the direction independent calibration. So that's when correcting for the instrumental systematics as well as the systematic from the ionosphere. This is sort of the same plot, but shown in the two-dimensional power spectrum space, which is very popular in EoR, where you have you can define these two regions known as the wedge and the window, and most of the effects can be seen to be in the window. In the wedge, but also there is an effect in the window, as shown in the previous plot, which was the one-D power spectrum of only the window only, and also at the moment, the third row is the level of calibration we usually apply for the MWA. But this plot, I think the takeaway message is that we can go even further using more calibrators and get even cleaner 21 centimeter 2D window with much less ionospheric contamination. But there's what we call the Ionosphere Nightmare, where around 50% of all the currently archived MWA data is active, and that means maybe it's not a good idea to use it in the EoR power spectrum. These plots shows a suite of 322 observations with all sorts of ionospheric activity. And actually, when we take half of the data, which has the least ionospheric activity, we see that it gives us a better power spectrum than using all the data. So that means we are better off not using half of our data. And in an attempt to solve that problem so that we don't lose all that half of all our data, there's this method where we can do our calibration and then use the ionospheric parameters to correct for the instantaneous ionospheric effect in our sky model, and then repeat the calibration with the new improved sky model, and hopefully that way we have dealt with the ionosphere. And on the top row, I'm showing the first and the second run of this process. And on the top right, you can see that all the ionospheric structure is dealt with, and we remain with a very sort of calm ionosphere with very small ionospheric offsets. And in the bottom row, I'm showing that this process, when we increase the number of calibrators, we actually now also running the risk of encountering more errors because of the reduced signal to noise ratio in the faint sources we include as calibrators there. And so this is just a simulation, but when I applied the same thing for the real data, so this is a quantification of how the offset errors increase with fainter sources in our sky. So applying the same method to real data, for example, this is a very calm ionosphere on the left, and on the right we can see that the method works really well, which tells us that the data before that we thought was actually good for, and we can use it, we can even reduce the ionospheric effect in it even further. And to add on that, with the very well data that we couldn't use before, the method also gives us hopes that maybe we can use it now. And that's also a good thing, because remember, now we can use the extra 50% of data we have. And that's good news for the EoR power spectrum. In conclusion, so I have a suit that now we can use to study the ionospheric effects on the power spectrum. And also, I think one of the main messages here is that these on-the-fly modification of the sky models based on the ionosphere can really help in mitigating these ionospheric contamination. And also, the next step is applying these to a lot more data that is active and seeing what effect we have on the power spectrum. Thank you.